We introduce a system for the deformation of an articulated object that is controlled by a skeleton. The deformation is put into the context specified by a small number of example meshes, which are given for some key poses of the skeleton. We begin by showing the deformations achieved by our method without the use of any example meshes. We compare our results to traditional linear weighted blending of transformations, the so-called SSD method. As you can see, our method produces much smoother and more natural results. The chest muscles contract naturally, although only the shoulder joints rotate. Notice the self-intersections near the scapula region and the overstretching of the shoulder area when SSD is applied. Existing skinning methods require an extensive setup process of rigging and weight tweaking. This is a tedious process which is almost eliminated with our method. The user first supplies a skeleton structure and a mesh of the object in its binding position. The user then roughly associates a group of triangles with each joint using a simple painting interface. Triangles in this group will follow the joint as it rotates. Triangles which are not associated to any joint will be influenced by the surrounding joints based on harmonic weights computed automatically by the system. In this model of an arm, we use only 3 joints. The shoulder joint is in charge of rigidly transforming the entire arm. The elbow joint is in charge of bending the arm, and the wrist joint is in charge of rotating the hand. A smooth deformation of the arm may be achieved by rotating the elbow and wrist joints. A main component in our computation is the mesh Laplacian matrix. This is factored by a Cholesky decomposition in a pre-process to allow faster real-time interaction. Factorization takes less than a second on the arm mesh containing 10,000 triangles. We now add one example to improve the deformation of the arm. This red example, which is different from the rest pose mesh, indicates to the system ever so slightly that the bicep muscle should bulge and the fingers bend when the elbow and wrist joints rotate. We add the example to our database. We then set the skeleton joints to a pose that fits the example pose. The system calculates the relative representation of the example with respect to the base mesh. When the skeleton is in the pose of the example, the deformed mesh interpolates the example mesh. Rotating the joints to a more extreme pose causes the mesh to extrapolate surprisingly far beyond the example mesh. Note the smooth and natural bulging of the muscle. When the wrist joint is rotated, the hand is rotated accordingly and the fingers bend correctly due to the example. The significant bend of the fingers is again a result of extrapolation of the small bend exhibited in the example mesh. The extrapolation happens only when the wrist joint rotates around the correct axis. When rotating around on any other axis, the hand deforms only according to the basic layer and is not influenced by the example mesh at all. Since the finger area incurs a significant rotation, skinning methods based on displacement fields, such as those of Lewis and colleagues and Sloan and colleagues, cannot handle such deformations correctly. The tips of the fingers shrink due to the linear nature of the morph. Cloth deformations that do not exhibit strong dynamic effects can be modeled with our system. We use 3 examples to guide the deformation of a shirt controlled by the spine joints. Here we see the application of our deformation technique to the shirt. This exhibits quite complex deformations with large local rotations. The example meshes which supply the context can occupy a large amount of memory. This can be a serious problem for many applications. We represent our examples in a compact manner using a small subset of the mesh triangles, so-called anchors. This is possible due to the smooth nature of the deformation in the example. Even when a very small amount of anchors are used, the fine geometric details of the mesh are preserved. we deform the straight armadillo leg into a bended leg by rotating the knee joint. On the left is the example mesh. When we ignore it, the mesh does not deform as expected and the muscles do not bulge. When we use the example, the results are improved. In the top middle image, we see the deformation achieved when all the triangles of the example are used as anchors. In the other images, different amounts of anchors were used, leading to less memory consumption and better performance. Note that the 2% anchor image is almost indistinguishable from the 100% anchor image, even though only 290 anchors were used instead of 14,606. Even when only 73 anchors are used, the fine scale details of the original mesh are still not harmed. When given a model of a plate with sinusoidal waves and one example of a 180-degree bend, the plane is perfectly deformed into the example and even extrapolated much further using only 30 anchors among 24,000 triangles.